Hi folks, welcome back to Physics with Captain Rod. The purpose of this video here is to be an introductory video or an introduction to the concept of vibration or harmonic motion. So what we're looking at here, imagine we got this mass spring system and the spring has a force constant K. And we're going to imagine that this mass is displaced a distance, maybe x sub o, and released from rest. And I'm going to talk about the subsequent motion and how to analyze it. So the first thing we would do, and I've already done this, is define a coordinate system. So I've called x the variable that I'm going to use to track the location of this object as it moves back and forth. I've got right positive. Now you notice that when I'm calling position 1 here, I put a subscript on this, x sub o, and that's because this is a fixed numerical value in this problem. This is a constant. This is the initial displacement of this particle. Now, vibration problems typically have what are called initial conditions, and the initial conditions are basically the conditions of the problem at t equals 0. So the first thing I'm going to do is write out those initial conditions. At t equals 0, the x value, the location of this object, is the value I'm calling x sub o. So I'm going to put at t equals 0, x is equal to x sub o. Also, the instant this thing is released, it's not moving yet. Right? When I let this animal go, it's definitely going to start accelerating to the left because the spring is going to be pulling on it to the left. But right at the instant it's let go, it's not moving yet. So the other condition here is that its velocity is 0 at that time, or in the language of calculus, we would say its time derivative here, x dot, would be 0. Now, these conditions are specific to this problem that I've made up. Other types of vibration problems might have other initial conditions. For example, maybe at t equals 0, the object may be at the origin, but moving to the left. In conditions like that, at t equals 0, your x value would be 0, but your x dot would be some numerical value and so forth. So these are going to vary problem by problem. All right, next, how do we analyze the motion? So the next step here after writing down the initial conditions is we have to derive what's called the equation of motion for the system. Now there's two ways we can do that, either by Newton's second law or by principles of work and energy, and I'm going to talk about both. So what I'm going to do here is I'm going to imagine this object at kind of an arbitrary location, but I'm going to put the picture down here. So somewhere in between here. And I'm going to say that the displacement now is what I'm just going to call x. And again, it's important to realize this would be a function. The spring would be applying a force in this direction, and that force, by Hooke's law, is proportional to x. Now, Newton's second law is a vector law, and let's think about when we write out a Newton's second law equation. If we say force equals mass times acceleration, well, in this example, the force is varying with x. The force will be a maximum at the endpoint and the endpoint on the other side, and this force would be 0 at x equals 0. So this thing's a function here. And because of that, we're not going to get a nice numerical answer out for the acceleration. We are going to get a function out for the acceleration and not a number. Right? So when you write your Newton's second law equation, it needs to be good on both sides. You'll notice that when this object is to the right, or in other words, when x is positive, the force is to the left. And also imagine that this object was over here now. The spring would be basically pushing on it to the right. So you'll notice that the force and the x value here has opposite directions. So what I'm going to do is I'm going to rewrite that force as minus kx. And the minus sign, what it does for me is whenever x is positive, this is going to give me a force to the left. And whenever x is negative, this is going to give me a positive value for the force. Now let me talk about some of the other forces that could be acting on this. Conceivably, we may have like a gravitational force, mg, surface and contact, so a normal force, and possibly a frictional force. And the frictional force is going to depend on the direction of motion. It could be right or left, really, depending on which direction this thing's moving. Now it turns out none of these forces, with the exception of the frictional force, are accelerating this object. And what I'm going to do in this example is assume the frictional force away. So we're going to imagine that this thing goes back and forth and moves without friction, in which case we really don't need any of these other forces. I'm just going to get rid of them. So when we write our general Newton's second law equation for this mass, what we're going to have on the left is minus kx equals m. Now I'm going to think about the different ways to write this acceleration. A is good enough if the acceleration is constant. So we might just, write A. However, in this example it's not. But other ways to write the acceleration would include dv dt, or because the velocity is the time derivative of position, we could also write d squared x dt squared. Now, if we write the acceleration term as dv dt, this is a three-variable problem, x, v, and t. So instead what I'm going to do is I'm going to write that equation in this form, d squared x dt squared. And there's my Newton's second law equation for this problem, written really as generically as I can. All right. Before I move on and talk about, what do we do with those equations, I want to talk a little bit about how we could, or another way to derive this equation. The other is by principles of work and energy. If we call this position 1 and this position 2, and again, the position 2, you got to imagine that this object is somewhere in between here. And I write out the work energy theorem, PE1 plus KE1 plus work equals PE2 plus KE2. Now, in this problem, the only relevant type of energies are elastic potential energies. Right? If I put a datum right through here, there are no gravitational potential energies in this problem. So the PE1 term is going to be a 1/2 k x sub o squared, because at position 1, x sub o is the distance that the spring would be stretched. System starts from rest. No external or non-conservative forces. Again, throwing out friction, we would have no work term, and the gravitational force and the normal force I had earlier wouldn't do any work because they're making a right angle to the velocity. PE2 can be written 1/2 kx squared, KE2 1/2 mv squared. Now, there's a very subtle but very important difference between these x values. This one is a constant. It's the distance that this was pulled from equilibrium and then released. This one is a function, and it's good on either side. When x is positive, it means the object is to the right. When x is negative, it's over to the left somewhere. All right. Now, this equation doesn't look anything like this. This equation is still basically algebraic in nature. And here's basically how it works. You give me an x, I can tell you a v. Or if you give me a v, I can tell you an x. But it doesn't give us time information. It doesn't tell us how long it takes to get here or there. Or it doesn't tell us another important factor that I'm going to get to later in the video about the frequency of the system. What I can do with this equation, however, to get time information out of it is we can time differentiate it, the whole thing. The left-hand side, when we take the time derivative of this, we get 0 because there's nothing in this equation here that's changing. When we take the time derivative of this term, we get kx x dot, or kx dx dt. And when we time differentiate this term, we're going to get mv dv dt, which is v dot. Now these equations, maybe they don't look quite similar yet, but we can do a little bit of messing around. X dot and the velocity are the same thing, so these cancel. So this now reads kx plus m. Now v dot, keeping in mind that v is x dot, or dx dt, that makes this x double dot. So these equations now basically are the same. Minus kx equals m. This is x double dot here. And here we have 0 equals kx plus m, x double dot. So other than the fact that this term is on the right, not the left, these are the same equations. So very important at this point in the video. You can derive these equations of motion one of two ways. Either by Newton's second law, or if you can write out a work energy equation for it and then hit it with a time derivative, you get what's called the equation of motion for the system. That's these guys. All right, so now I'm going to talk a little bit about what do we do with those. So hopefully you've watched my video on differential equation theory. Standard thing to do is to write highest derivative first with a 1 in front of it. So I am going to get rid of this stuff because I don't need this anymore. Basically get rid of all of this. Alright, we're going to take this guy, just going to lift that up there. Alright, highest derivative with a 1 in front of it. If I do that, what we're going to have here is d squared x dt squared plus k over m times x equals 0. And I got that, you would get that just by maybe adding this term to the right and dividing by m. Now, this equation is a very special type of equation. Notice that x here is some function, and this equation is saying that hit that function with 2 derivatives, add it to some number times itself, and you get 0. There's only one type of function, or I guess we'll say 2 types of functions in the entire universe that exhibit that behavior, that you can hit with 2 derivatives, add them to themselves, and get 0, and those are sines and cosines. So a sinusoidal function will solve this. So will a cosine function. And there's a theorem in differential equation theory about equations that are called linear differential equations. And this is an example of a linear differential equation. And that theorem is this. If you have 2 functions, let's say y1 and y2, that both solve this equation, the sum of the 2 also solves it. So y1 in this example might be something like a sine of bt, some sort of kind of generic trig function. y2 might be some other function, a cosine function, maybe a c cosine of dt. It's pretty easy to show that either one of these can solve this equation. The sum of the 2 will also solve it. So this equation has a general solution. X equals, oops, and I'm sorry, I went from y's to x's here on you. I guess what I meant here really was x's. Sorry about that. In the equation I wrote, x is the dependent variable. And the general solution for x looks something like this. Okay? Now, general solutions are, this is a solution to any equation basically of this mathematical form, where I have a function differentiated twice, added to a multiple of itself, and then you get 0 out of it. So the million-dollar question now is how to get constants a, b, c, and d. Now it's pretty easy to show, and I'm not going to do it right now, but it's pretty easy to show that whatever b is and d, these will end up being the same numerical value. So what I'm going to do is I'm going to rewrite this. X equals a sine, and I'm going to write this omega t plus c cosine omega t. Now, why did I call this omega? Well, it turns out that this quantity here, if you look at it carefully, it has units of radians per second, and that's what's called your angular frequency, kind of similar to angular velocity. So it's pretty common to use the Greek letter omega to represent angular frequency. Now, solution of these types of equations. So if you have initial conditions, I always recommend that you apply them, particularly if you have a 0 initial condition. So right here we have a 0 initial condition that at t equals 0, the velocity of this object needs to be 0. So what I'm going to do is I'm going to apply that condition. To do that, however, I need to calculate the velocity of this object. This function gives me the position. Its velocity is given by the time derivative of this equation. So this is going to read, let's see, time differentiating this, a omega cosine omega t minus c omega sine omega t. And all I've done is went through and differentiated this function, derivative of sine being cosine and the derivative of cosine being minus sine. But don't forget it needs to be chain ruled, so these terms have to come out in front. So what we're going to have next is, next thing to do is to apply this condition. When time is 0, the velocity has to be 0. So this is going to read 0 equals a times omega times 1. The 1 is coming from the cosine of 0. minus c times omega times 0. And the 0 is coming from the sine of 0. And you notice that this term is gone. And by inspection here, looking right here, we have a times omega equals 0. So this has two possibilities. Either a equals 0 or omega equals 0. Now, the omega, these guys are called angular frequencies. We can't allow this. If I put omega equals 0 into our solution here, this reads x equals 0 plus c, because the cosine of 0 is 1. And oddly enough, I mean, it will actually get something, I think, that'll solve this, but this is not the one we want. A lot of times these equations have what are called the trivial solutions to them. And if the omega is 0, we have what's called the trivial solution. It will actually solve the equation, but doesn't physically represent what's going on here. So this is the one we want right here, a equals 0. And by doing that, what we have is that our solution here can be updated to x equals c times the cosine of, again, omega t. I'm using this form right here, where the constants c and omega still need to be determined. So I think what I'm going to do is stop this video at this point. Just call this part 1, because I see it says 16 minutes. I'd like to keep it shorter than 12 if at all possible. And in the next video here, I'll talk about, all right, well, how do we get the c and the omega, and how do we get what's called the angle, the frequency of the system, the vibrational frequency of the system. So I hope that you enjoyed this video, and stay tuned for part 2.